Hi, this is Vikramjit from the Arch Lab at UCSB. I've been working with Professor Sherwood and Mohit Tiwari to build the first working prototype illustrating complete information flow tracking from the gates up. So what is this new information flow tracking technique that has me and my colleagues at the Arch Lab all excited? Well, the authors of this paper essentially propose a new microarchitecture which for the first time provides the ability to account for all information flows through the chip. That's right, all. Since all information is being tracked, this implies that it will be impossible to change data marked as trusted without being noticed. Not even the exploitation of covert timing channels will go unnoticed. To top all that, this technique goes one step further, as it changes the notion of how trust values are propagated. Traditionally, information flow techniques have suggested that any use of untrusted data should lead to an untrusted output. Right? Probably not. This is because if you go down to the gate level and examine closely, it turns out that this approach is overly conservative. For instance, take a simple AND gate. If one of the inputs of the AND gate is 0, the output of that AND gate will be 0, irrespective of the other input. What this translates to in terms of information flow tracking is that the output of this AND gate for this case can be trusted irrespective of the trust value of the other input. This is precisely what the figure on the screen attempts to explain. For the figure shown, a trust value of 0 indicates trusted and a trust value of 1 indicates untrusted. At this point you're probably thinking how we formalize this notion of information flow tracking from the gates up. This is how we do it. For every gate in the circuit, we introduce additional logic which computes only the trust values. And this is how it looks right now on your screen. You're probably thinking that this is impossible. No, not at all. Shortly I am going to show you this principle implemented and working on an FPGA. Moreover, I am currently working on prototyping a complete processor based on this principle on an FPGA. So there is nothing impossible about this technique. Just to briefly illustrate, the figure on your screen shows how a simple mux can be built using the technique discussed so far. So without any more delays, let's proceed to my implementation of complete information flow tracking from the gates up. The figure you see on your screen is a time donation arbiter augmented with shadow logic to carry out information flow tracking. For simplicity, only a high-level view of the shadow logic has been shown. As can be seen in the figure, for each gate in the circuit, there exists a shadow gate which is responsible for correctly identifying whether and how trust values propagate in the circuit. More about this during the actual demo. So finally, let's see that arbiter in action. So what you see right now is the arbiter we saw a moment ago. And before we proceed to see how the information flow tracking actually works, let us quickly verify that this arbiter indeed works as described before, along with all the shadow logic. The present case where both requests are low shows how cycles are being donated from the low CPU to the high CPU. Now let's consider the next case where request H is high. As expected, due to cycle donation, grant H is always high. Now moving on to the third case. Here we can see that no cycles are donated. Finally, the last case where both the requests are high and the arbiter alternately grants requests to both the high and the low CPUs. Finally, let's see that information flow tracking in action. The 10 bits are represented by respective decimal points in the 7-segment display for that signal. Consider the first case. Here request L is tainted. So now here is the beauty of information flow tracking from the gates up. Since the clock is high, there is no way that grant low can be affected. So even though request low is tainted, grant low is still trusted. Also, since there is no path, or speaking more precisely, no cycle donation from low side to high side, grant high can also be trusted. On the other hand, when the clock goes low and grant low can be affected by the tainted low request, grant low is marked as tainted. Moreover, since there is a path of cycle donation from the low side to the high side, grant high is also marked as tainted. So maybe that explanation went a little too fast. Let's see that again with some frozen frames. So as you can see, the clock is high. Since the clock is high, its effect will not be propagated through the rightmost AND gate to grant low. This is shown by the green path terminating at that AND gate. Traditionally, the output of this AND gate would have been marked as tainted. This is where gate level information flow tracking is different from the traditional approaches. Since one of the inputs is 0, it does not matter if the other input is tainted or not, as nothing will be propagated. The AND gate will be stuck at the value of its controlling input. Something similar is happening for grant high as well. Since the clock is high, the middle AND gate is disabled. So for this cycle, what the high CPU does is, in one sense, secret, and the low CPU can never affect or know what is happening at the other end. As you can see, the blue and green lines terminate at the AND gate, the middle AND gate, and nothing is propagated from the low side to the high side. I hope the power and beauty of this innovative approach is now coming to light. Now as you can see in the figure on the bottom right of your screen, the clock is low. Since the clock is low, the rightmost AND gate is active. That is, the output depends on the value of request low. However, since request low is tainted, this output is also marked as tainted. This is indicated by the green line passing through the rightmost AND gate, which shows that this AND gate is enabled. The low clock also enables the middle AND gate, that is, it enables cycle donation from the low side to the high side. But since the value of request low is tainted, grant high can also not be trusted. Again, the paths formed have been shown by appropriate colors in the figure. Let's consider one more case. In this case, request H is tainted. So for a high clock, grant H is tainted, and since there is no cycle donation from high to low, grant low is trusted. On the other hand, when clock is low, there is no way request high can affect grant high, and since a cycle is donated from the low side, it is trusted. Okay, so now since there are two inputs with two taint bits, the number of cases to be considered is fairly large as far as explaining all of them in detail is concerned. I can already imagine some of you frowning with me mentioning this, thinking there are probably some cases for which my prototype does not work. So, to accommodate best of both worlds, I have included footage for all the cases, and you are most welcome to analyze and verify them for correctness. So just to reiterate, you witnessed the first working prototype of complete information flow tracking from the gates up as applied to a time donation arbiter. Thank you for your interest in this research. Bye-bye.